Hello everyone, welcome to Deep Learning Talks. Large language models. The large in language models or the large and large language models has changed by orders of magnitude as we evolved from the early GPT models, the early language models to today's models, right? So we're going to discuss today about large language models, the scaling laws, and more nuance on how things have changed and progressed as we have moved from the early GPT models to today's GPT models. We have learned to define a large language model. Mathematically, we have derived that they are probabilistic models. They are function approximators. They are nothing but neural networks. And these kind of neural networks help us in predicting the next token, right? And when we put them in a loop in an autoregressive way, they keep on predicting the next token, token over token, token over token, so that we can visualize them as autocomplete. We can visualize them as conversational. I mean, they're not directly conversational. We have to enforce the conversational behavior by training them on massive conversational data sets. So just imagine that we have a neural network that is the next token predictor. So that neural network is known as a transformer. That neural network internally uses the architecture of a transformer, or at the lowest level, it is a math equation. One level above, it is a transformer. One more level above, we have abstracted it out as, and we are just calling it a neural network. One more level above, we are just calling it a language model, right? And one more level above, we just call it an application, right? So if we talk about at a neural network level, we have one neural network, let's say f of x, that predicts the next token. We have another neural network, let's say g of x, that has been trained to make conversations. It's like, imagine a lot of people wrote or a lot of manual data labelers wrote a lot of conversations to make the f of x neural network conversational in nature. The f of x neural network is a simple generative decoder only transformer at a sub level, but we trained another g of x to on millions of conversations to make the neural network conversational, because the neural networks were not intrinsically inherently conversational in nature, right? Why did we make it conversational? Because we wanted to mimic as if a human is talking to you. We wanted to mimic as if a brain is there at the back of the application who is thinking and reasoning about all your questions. We didn't really, or we didn't only wanted a fill in the blank mask language model, or we didn't a simple autocomplete model, right? We wanted a conversational AI, because conversational AI has real use cases, right? So now let's keep it aside. Now we know that at the lowest level we have bunch of equations and some statistical probabilistic models. Then we encapsulate them and wrap them in an architecture which we call as transformers. And just to abstract out transformer, we simply call them neural networks or function approximators. And we wrap them around in an application that is exposed to an end user, and we call it Chat GPT, we call it Geminis of the world, right? Now let's keep this aside. Now let's talk about why large and what has happened, how have we evolved. So when GPT-1 was released versus today, we're standing at 26, early 26, we are working with the GPT family where we are standing at GPT-4 and GPT-5. When GPT-1 was released versus now when we're standing at GPT-5, have we innovated a lot? Have we as human beings become a lot smarter in research, that there's drastic amount of difference in GPT-1 and GPT-5? I would say not really. Theoretically, what we have theoretically and applied both, what we have done is we have scaled data, we have scaled compute, and we have scaled the model complexity or the number of parameters, right? So these three pillars, the first pillar is data, the second pillar is compute, the third pillar is parameters or model complexity, not necessarily in this order, has have dramatically gone up from the evolution of GPT-1 to GPT-5, right? So this has improved a lot. This has what has been really changed. So scaling laws says that when you increase these three parameters, or basically there is a high correlation that when you increase the amount of data that you are training your neural network on, when you increase a lot of computing flops, computing units that you are training your neural network or large language model on, when you increase the model complexity by adding in more and more layers, by adding in more and more subcomponents or sublayers, that internally increases in the number of parameters, then the performance increases. Performance increases, that means your loss decreases, your performance increases, your language model gets better at generating more and more coherent and contextually relevant text. So this is what the scaling laws says, and scaling laws have worked tremendously well. If we just look back in retrospective to do a small sanity check. So if we just compare the first early GPT model, let's say the GPT-1, and today's GPT, which is the GPT-5, with respect to all of these three parameters. So the first parameter that we talked about was data. So it was trained on a couple of GBs of data, and it was trained on 117 million parameters, the first GPT. Now we are standing at not 1 billion, not 10 billion, but hundreds of billions of parameters in the latest GPT-5 models, and maybe a trillion, right? So we've gone 10,000 and 100,000x in a lot of ways. Similarly, if we talk about compute, the training of GPT-1 took 10 raised to the power 19 flops, and right now we are spending 10 raised to the power 25 flops. Similarly, if we talk about the money that we have spent, the training cost and the infrastructure cost, we used to spend thousands of dollars, couple of thousands of dollars, while we were making GPT-1. Now we are spending 100 million to $1 billion in the training and infrastructure cost. Similarly, if we talk about GPU, we were only spending some dozens of GPUs in the GPT-1, and right now we are spending 10,000 plus GPUs just to train a large language model like a GPT-5. So in retrospective, we can see that the jump from GPT-1 to GPT-3 to GPT-5 was not, 10x. It was 10,000s and orders of magnitude more than 10x. It was hundred thousands of x, and with respect to compute and with respect to the number of parameters that we have scaled. So these, are nothing but what define the scaling laws and what makes the large language model dramatically large. Along with this, if we try to plot the early language models and today's language models on a log scale graph, we would see that early language models basically are flat near zero, right? So it does not mean that they were useless. They helped us invent the transformer architecture. They helped us experiment with the transformer architecture. If we didn't have transformer architecture, then all of these scaling laws would also not have worked out. So we wanted an architecture, and we wanted to test our hypothesis of predicting the next token in an autoregressive way, which went on really well. But then when we applied scaling laws, when we scaled with respect to data, with respect to compute, and with respect to the model parameters, we saw tremendous results. And those results have given rise to a trillion-dollar economy, which is the current AI economy, right? So we can also say that we didn't really, discover intelligence, in the 2020s or 2025. We just scaled things better. We finally had enough amount of compute to expose what neural networks were capable of doing, and the mathematical equations and the fundamental model, the architecture has always been the same. It's just our potential to spend money, invest money in the training, and scale very well on all of these three parameters to see the kind of results that we are seeing today. Now, the insides of the language model. Just let's take a brief on the insides of the language model before we dive deep into it. So the insides of the language model are still the same. So we have a lot of text that a language model sees. All of that text gets converted into tokens using a using a tokenization algorithm, and that tokenization algorithm also acts as the first algorithm that gets run on the data, obviously after all the pre-training happens. So okay, so since we are introducing the word pre-training, let me also talk about pre-training. So whenever we talk about pre-training, the very key important part is the data collection. So it's like we have scraped the whole internet, all the web pages, all the text on the internet at one place, and we have filtered out all the useless stuff, right? All the racial comments, all the pornographic content, all the spam and malicious websites, and we have kept all the juice or the knowledge that represents all of world's knowledge, right? So the internet data is assumed to represent all the world's knowledge, and we are trying to build a function approximator that can, you know, act as a simulator on that knowledge, that can act as a generator on that knowledge, that can act as a generic brain, not a biological brain, but that can act as a generic engine that understands or has the potential to represent that knowledge in some higher dimension, right? So this is what large language model is. Now, since pre-training is a lot about data collection and filtering, the filtered text and all the data that has been collected after pre-training goes into a tokenization algorithm that gets tokenized. we get discrete token IDs. Along with that, we need something which is continuous, which is the token embeddings, right? So a large language model is nothing but it has a lot of token IDs for all the tokens, then token embeddings, then obviously the transformer that takes those embeddings as input along with positional embeddings. Then what transformer produces is nothing but logits or probabilities. We use them interchangeably. Then we sample from the probabilities. For example, let's say it has generated X amount of tokens, and for each of those tokens, it has generated certain probability or logits. Now we sample from that probability distribution. Let's say we take an argmax function to predict the maximum probability, or we sample randomly from the output head or the generated probabilities to generate or to predict the next token. So this is what goes in the internal of a large language model and the pre-training part. And this is what the scaling laws were and how we have evolved from the first early GPT model to today's GPT model. In the next upcoming videos around large language models, we'll discuss more and more nuance on the feed forward pass of a large language model and the backward pass, the training, and yeah. And obviously, we'll also have a lot of discussion on inferencing, right? So training is important, pre-training is important, inferencing is also very important. The stochastic and probabilistic nature of a language model during inference time is also very important. So we'll discuss it in the upcoming videos. Thank you.